What's the deal with stars? Am I right? They're beacons of hope to many, or in other cases, just blips of light millions upon millions of miles away from us. For many people in the past and the future to come, stars have been the guides used to navigate the globe and have helped to further our understanding of the universe as we know it. They are responsible for the formation of not just our little blue planet, but every other planet in the universe as well. Unless, you're one of those starless planets. We don't talk about those guys. Freaking weirdos. They're the source of plenty of magnificent sights, with views that are unrivaled by basically everything in nature. Though with that beauty there comes a certain lingering danger. Today we're going over the life cycle of stars. How they form, how long their lifespan is, how they differ from each other, why they get to rank our hotels, and what happens when they die. Alright, let's get started. Now, first off, what warrants being a star?
No.
Okay, now we're talking. Get into the nitty gritty. Actual stars are heavy, huge, and hot. Their masses can range from 0.05 to over 50 solar masses. Their sizes can range from 450 times smaller than the Sun to over 1,000 times larger than it. Their surface temperatures can range from 3,300 degrees Kelvin to over 50,000 degrees Kelvin. And taking a look a little deeper into them shows that their cores reach millions of Kelvin.
Oh, that's hot. That's hot.
Now that we got those out of the way, on to the big guys. Corner number 1, boom, dwarf star. Corner number 2, boom, average star. Corner number 3, boom, massive star. Whoa, yeah, camera share, I'll tell you that much. And in corner number 4, introducing a whole lot of dust. I mean a lot of dust. Ugh, you gotta love dust. So, yeah, dust. Apparently, and unfortunately, not even the vast reaches of space can escape its allergenic clutches, as it's everywhere there too. But with a little bit of counseling from gravity and gases, a whole lot of dust can come together to turn over a new leaf as a star. But we're getting a couple stages ahead of ourselves, so let's start at the beginning of this whole star cycle. At stage 1.
No way.
Just as a heads up, these stages are vague and unspecific about exactly when and for what reasons they start. So there's not much to say about some of the stages, and it's likely that not all of us will see eye to eye on some of them, depending on your sources. But I'm the guy making the video, so for the time being, my opinion matters more than yours.
Dr. Bell, this is a joke. Please don't dock points for my grade.
Stage 1 starts off with clouds of dust. These interstellar clouds, also called nebula, can Stage 1 starts off with a bunch of clouds of dust. That was just a bad take. Wait, where was I? Stage 1 starts off with a bunch of clouds of dust. These interstellar clouds, also called nebulae, can span tens of thousands of parsecs and contain thousands of times the mass of the Sun. Anyways, for one reason or another, the nebula begins to contract under its own gravity and fragment into smaller pieces called, you guessed it, fragments. Stage 2 has the individual fragments start to collapse, and once their density is high enough, no more fragmentation will occur. Stage 3 has the core of the fragment begin to heat up to around 10,000 Kelvin as it contracts. It will continue to heat up until at about 10 million Kelvin over the next few stages. Stage 4 has the core become a protostar, with it having its first HR diagram appearance. Aww. Well, that's going on the fridge. Stage 5 has planetary formation begin around the protostar's disk, though the protostar isn't in equilibrium yet. Stage 6 marks a turning point for our protostar as the core has reached 10 million Kelvin, meaning that nuclear fusion has now begun to occur and thus our protostar has now become a star. During this stage, the star is still contracting and getting hotter. And to top things off, in stage 7, our star enters equilibrium, which means that the force of gravity trying to collapse the star is balanced out by the pressure of nuclear fusion, pushing the star's gas outwards. Due to equilibrium, the star won't contract anymore and will stay at relatively the same size for a long period of time as a main sequence star. The main sequence is where stars spend 90% of their lives on as stars, and they will stay on it for as long as they have hydrogen to fuse into helium. And they've got plenty of that to go around. While these stages are generally how every star begins, the way every star ends isn't nearly as set in stone. What remains of stars and how long they last for depends mainly on the mass they accumulated in their formulation while entering the main sequence. The rate at which stars consume their hydrogen supply is dependent on their mass, with stars that have higher masses consuming the hydrogen faster in comparison to stars with lower masses. This means that even though larger stars obviously have more hydrogen to fuse than smaller stars do, the rate at which larger stars go through the hydrogen is much faster, which leaves them with a far smaller lifespan. Another aspect of stars that mass influences is what they end up being in their old age, as you'll see coming up. To start off with, and seeing how it's the one most important to us, let's talk about the future stages of stars with similar masses to our own. These stars will last for around 10 billion years from start to finish. After running out of hydrogen in the core, gravity once again takes over and causes the core to shrink and get hotter, the heat flowing outwards to the outer layers where some residual hydrogen remains. And seeing how it's gotten hot enough in those layers, fusion can now occur in them to fuse hydrogen. This fusion causes the outer layers to expand into what we call a red giant. Eventually, though, this red giant will run out of fuel to fuse, which will cause it to collapse under gravity and lose its outer layers as they expand outwards into space, forming a planetary nebula. The remaining core of the star is called a white dwarf star, which over time will cool and dim, and once it stops shining, it will become a dead star known as a black dwarf. Something weird about black dwarfs is that they're only hypothetical, since they don't exist yet in the universe due to not enough time having passed for a star to have reached this final stage yet. The smallest type of main sequence stars are called red dwarfs. Red dwarfs last for trillions of years on end, meaning that they'll be the last star left before the universe goes dark. This is mainly due to their very small size, granting them a very, very long lifespan, and them staying convective, which means that the helium and hydrogen throughout the star constantly mixes like this. So these stars use up their fuel incredibly slowly before finally running out of it. Once its hydrogen does run out, and most nuclear fusion reactions stop, the red dwarf will shrink into a blue dwarf and gradually burn out completely. At this point, it has no source of energy and will become a white dwarf, with it cooling extremely slowly and ultimately becoming a black dwarf. To finish things off, let's talk about the biggest main sequence stars out there, the massive stars. Due to their large size, massive stars have a rather short main sequence lifespan that clocks in at millions of years, after which they go through a stage similar to the one that our own star will go through after leaving the main sequence, and then it will become a red supergiant. The lifespan of red supergiants is measured in millions of years instead of billions or trillions, as their large size means they expand and go through their fuel supply at a very vigorous rate.
Okay, come on. Oh, yes! Yes! Yes!
Luckily for them, though, in their cores, red supergiants have the mass and thus the pressure and heat necessary to continue the fusion process to mix heavier elements together, which is a luxury other smaller stars can't use nearly as well to the same extent. Though this process will end eventually, with these stars tapping out when fusion turns their core into iron, which makes them unstable and collapse in under a second, with the incredibly high temperature and pressure turning it into something that would bring Michael Bay to tears. These massive explosions are called supernovas, and they're often brighter than the trillions of stars in their own galaxy. Ironically, it's the death of these stars and the matter they expel far, far out into space that gives birth to other stars like our own, which in essence has one generation of stars pass on the baton of birth and death to the next in what's by far the longest relay race ever in the universe. After the supernova occurs, the star's remains will either form a neutron star or a black hole depending on the mass. If the surviving core has a mass of 1.5 to 3 solar masses, it will become the quickly rotating and mind-bogglingly dense neutron star. If the core has a mass of more than 3 solar masses, then it will become so dense that it collapses in on itself and rips through the fabric of space-time to become a black hole. Black holes tear through anything close enough to them, and not even light can escape them, which makes them invisible to our eyes. Not to mention, we have a supermassive black hole at the center of our galaxy. Comforting stuff, I know. And boom, there we go. That's everything you need to know about stars. Oh.
Get the hell out! Get out! Get out!
And that's a wrap.